welcome again to my Physical Science online lecture supplement series. In today's video, I wanted to work a few examples that are supplements to the textbook Introduction to Physical Science by Shipman, Wilson, and Higgins. These go with the chapter concerning waves and sound. So as always, it's a good idea before we start the examples to go ahead and review a few of the equations that are introduced in this chapter and in my notes. So the first equation is the frequency period relationship. The second one relates wave speed to wavelength and period, or also to wavelength and frequency. The third one gives the speed of light in vacuum. This is an approximation to 3 significant figures. The fourth one is maybe the scariest looking of the equations that we have here. This is the equation which tells us what intensity is. It's power per unit area, which is energy or work per unit time per unit area, and the consequence of that is that intensity times distance from source squared should be constant so long as the energy is being conserved as it propagates outward from a source. Okay, so let's look at a few of these examples. Okay, first example says that we observe waves in the ocean arriving upon the shore once every third second, and the question is, what is the period and the frequency of these waves? So here you see these waves. They're arriving once every third second. So this one arrives, we time it, then this next wave arrives 3 seconds later, then this one arrives 3 seconds after that, and so on. Now the period tells us how much time elapses over the course of one wave. In other words, the period actually is the time that it takes to get from one wave to the next wave. So if the waves are arriving on the shore every third second, then that makes the period of the waves 3 seconds. So we can write, for example, that t is equal to 3 seconds. And the other question was, what is the frequency of these waves? So the frequency, you'll recall, is related to the period by f equals 1 over t. So this would be 1 over 3 seconds, or 0.33 inverse seconds. And this unit of inverse seconds is sometimes called a hertz. So 1 hertz is the same thing as 1 wave per second, or 1 cycle per second. So our frequency can be given by 0.3. Since we only had one significant figure, I guess you'd just say 0.3 hertz. Though if we have more significant figures, then we can just add some more 3's after that. So period is 3 seconds, frequency is 1/3 of a hertz. Second example for these chapter 6 examples is that we're given sound travels at approximately 344 meters per second in air. That is the speed that's given by your textbook. Most sources, by the way, give 343 meters per second. It's actually temperature dependent. What is the wavelength of the sound generated by a 512 hertz tuning fork, first harmonic only? This right here is your 512 hertz tuning fork. Sometimes they're labeled 512 CPS for cycles per second. All right, so we wanted to find the wavelength. So that's represented by lambda. And to do that, we have been given the speed at 344 meters per second and the frequency at 512 hertz. And so we have this equation that says that the speed is equal to the wavelength times the frequency. So if we rearrange that equation, that means that the wavelength is going to be equal to the speed divided by the frequency. So our wavelength must be equal to 344 meters per second divided by 512. I'm going to go ahead and just write this as per second, because then it's more obvious that the per seconds cancel. And this is going to therefore give us a wavelength in meters. So let's go ahead and do this by putting it into our calculator. 344 divided by 512 gives us 0.671875. So our wavelength here, 0.671875. And in fact, we only have 3 significant figures to work with, so that means that we need to actually write our wavelength as about 0.672 meters. So that's the wavelength of the first harmonic wave that's being generated by this tuning fork. So our tuning fork is generating sound waves of length 0.672 meters. Our third example for this chapter gives us waves traveling on a string. And we're told that the distance between adjacent waves is 2 meters, and that they're arriving once every 4 seconds. So we want to know what's the wave speed. By the way, this image that I'm showing here is standing waves on a string. This isn't necessarily the picture that you need to have in mind when doing this, although a picture like this can be used. One whole wavelength, by the way, on this picture is described by this right here. So this right here, one up, one down, actually is one whole wavelength for what it's worth. If you want a slightly different picture, you can imagine there being a string that is carrying a pulse, and then some distance ahead there's a second pulse. And the information that has been given to us is that there's 2 meters between consecutive waves, or between consecutive pulses on the string. So this distance right here would be 2 meters. And the amount of time that it's going to take for this guy to get from here to here has been given by 4 seconds. Okay, we're assuming though that these are actual waves that are arriving sort of like ocean waves here. And so this delta t actually is the period. So this is period, for which we often use a big T. And what we're looking for again is the speed of the wave. So speed is going to be the distance over time. So the distance that we have to work with is a wavelength. The time we have to work with is a period. So that gives us 2.0 meters divided by 4.0 seconds. So this is 0.5 meters per second. So that means that the wave speed in this case is 0.5 meters per second. Okay, another example. This is the fourth example for this chapter. You have waves on the surface of a certain lake. It's actually Lake Clark. And they're traveling at 6 meters per second. So that's the speed that these waves are traveling at. And we see that there's 4 meters between each crest and the next crest. Okay, so that means that if you had a way of measuring the speed at which these waves are propagating, you would get 6 meters per second. And meanwhile, if you were to maybe stand out here with a string, and you have one person standing at one wave and you have another person standing at the next wave, and you stretch out the string and you measured out the length of that string, you'd get 4 meters between consecutive waves. So the question is, what we want is period, which is represented by T, and frequency, which is represented by an F. So we have this equation that says that speed is wavelength times frequency. And so if we're solving for the frequency, that means that frequency should be equal to speed divided by wavelength. So we were given a speed of 6 meters per second, and we were given a wavelength of 4 meters. So if you need to use your calculator to solve this, you would plug in 6 divided by 4, and you would get 1.5 as your answer. So frequency is equal to 1.5, and for the units we notice there's an M and an M, so there's a per second. So per second is the same thing as hertz. Okay, the next thing that we wanted was to get the period. So recall that period and frequency are reciprocals of each other. So the period is going to be 1 over 1.5 inverse seconds. So again, you'd want to throw that into your calculator. In my calculator, I can just push this button. That gives me 0.6666 repeating. So the period is about 0.67 seconds. Okay, and those are both keeping track of the number of significant figures that we should have. So again, the waves have a period of 0.67 seconds and they have a frequency of 1.5 hertz. So every 0.67 seconds one of these waves is arriving at the shore, and 1.5 of them are arriving every second. Okay, example 5 for this chapter asks, what is a typical wavelength for microwave radiation? So if you wanted to figure out what the wavelength of microwave radiation is, there's actually a way you can do this experimentally that's kind of neat. Basically, you can stick some small object in the microwave, either in the middle or off to some side, turn it on, see whether the thing is heated much or very little per unit time. If it happens to be at a point where two waves interfere and you get a very weak amount of heating, then you are at what would be called a node. If you are somewhere where there's a very strong amount of heating, you'd be at what's called an antinode. Okay, that is basically equivalent to noting that the microwave is basically creating a standing wave with light that looks kind of like this standing wave on this string from this earlier example, 6.3. So if you put the thing you're trying to heat somewhere where you get an interference like this, you're not going to get much heating. If you put it somewhere that looks more like this, you end up getting quite a bit of heating. So you can put some objects in the microwave and try to measure, okay, I'm going to put a very small object in, not very much heating was done, I'm going to move it over a couple centimeters, a little more heating was done, I'm going to put a new object in, move it a couple more centimeters, a lot of heating was done, move it a few more, new object, and so on. And by measuring how far apart you have to place one small object and another small object, you should be able to basically locate how far apart the antinodes are. This works better, by the way, if you take the microwave tray out so that it doesn't rotate the object around the microwave. You want it really to sit stationary, so that kind of tells you something about why there might be a little rotating tray in the microwave. In any case, once you've measured how far apart these two antinodes are, you now have what is equal to actually half the wavelength of the microwave radiation in your microwave. So you double that distance and now you've got the full wavelength. Okay, there's also a theoretical way of estimating what the wavelength of your microwave radiation is. For example, most microwaves will actually tell you the frequency that they are operating at, so you can use that and the speed to get the wavelength. If you just want to get a rough estimate for what the wavelength of a microwave radiation would be, you could look in your textbook, which shows the frequencies of the electromagnetic spectrum. And specifically what we're looking at is microwave radiation. So you see that this thing is saying that microwaves are at roughly 10 to the 10th hertz, or 10 to the 10 cycles per second. So frequency is approximately 10 to the 10th hertz. You know that electromagnetic radiation, light for example, but microwaves as well, has a speed which is given by 3.00 times 10 to the 8th meters per second. So the equation we've been using has said that speed is equal to wavelength times frequency. Well, for light we actually use a c to represent the speed. So we would write that c is equal to lambda times f. And so the result is that the wavelength should be that speed divided by that frequency. And so that is 3.00 times 10 to the 8th meters per second divided by 10 to the 10 seconds inverse. So the seconds inverse cancel. 10 to the 10th and 10 to the 8th. So 10 to the 8th, when you have something like this, 10 to the 8th over 10 to the 10th, that's going to be equal to 10 to the power of 8 minus 10. So in general, if you have x to the a over x to the b, the answer is going to be x to the a minus b. And similarly, if you have x to the a times x to the b, that should be x to the a plus b. Okay, so this right here becomes 10 to the minus 2. So the wavelength, therefore, is approximately 3 times 10 to the minus 2 meters, or 3 centimeters. So an order of magnitude estimate gives that a microwave has a typical wavelength of 0.03 meters, 3 centimeters. For what it's worth, I went and looked at the back of the microwave that I have sitting in my office, and it says that it operates at a frequency of 2,450 megahertz. So 2,450 megahertz means that we can say 2.45 times 10 to the 9 hertz. And so if we were to repeat that calculation that we just did, which says that C is equal to lambda F, and therefore lambda is C over F, we end up getting that lambda is 3.00 times 10 to the 8 meters per second divided by 2.45 times 10 to the 9th per second. And so if you plug those into your calculator, 3 divided by 2.45 would give us this number. We have 10 to the 8 divided by 10 to the 9, so we need to multiply that by 10 to the negative 1. And so you end up with 0.122 meters. So the microwave in my office has a wavelength of 0.122 meters, or 12.2 centimeters. What this means is that if you were to use the microwave that I have in my office, which is just a standard microwave that I bought at Walmart, nothing special about it, you should be able to find one of these antinodes every half wavelength. So, divide this number by 2, you get 0.061. So every 6.1 centimeters you should find a node, and every 6.1 centimeters you should find an antinode. That also means that this experiment that I described earlier is fairly straightforward to do in the microwave. So you can try this at home sometime if you'd like. Just don't use anything metal or something that's going to explode in the microwave. Okay, our next question, what is the typical wavelength for an X-ray? So to answer this question, we should go back to this chart that shows the order of magnitude of each frequency for each part of the electromagnetic spectrum. Again, this chart is basically figure 6.7 in your Shipman, Wilson, Higgins, and Torres Physical Science 14th edition textbook, figure 6.7. So the question was asking about X-rays. So we have the X-rays have an approximate frequency of 10 to the 18 hertz. So frequency is about 10 to the 18 hertz. And of course, this is again electromagnetic radiation, so the speed is 3 times 10 to the 8 meters per second. Those are both given. So C is equal to lambda times F, and therefore lambda should be C over F. So that is going to give us 3 times 10 to the 8 meters per second divided by 1 times 10 to the 18 per second. So again, the per seconds cancel, and what you end up with is 3 times 10 to the 8 minus 18. So that's 3 times 10 to the minus 10 meters. So our wavelength for an X-ray is actually quite short, less than a nanometer here, about 0.3 nanometers in this case. 3 nanometers, as a double check, you know that an X-ray is much, much shorter than the visible light. And for visible light, your textbook actually gives a range from about 400 nanometers to about 700 nanometers. So this is about 3 orders of magnitude shorter than that. Okay, so the 7th example for this chapter is about a helium neon laser. So this is actually one of the early gas-based lasers that they actually were able to make work and stay on, if you will. So a helium neon laser has a typical wavelength of 632.8 nanometers, red basically, and you can kind of see it glowing a sort of reddish color in this photo. What is the frequency of this laser's radiation, and what approximate color is it? Well, you can see that it's red from looking at the photo. The question though is also, what frequency is this? So frequency is unknown. The wavelength was 632.8 nanometers, which is the same thing as 632.8 times 10 to the minus 9 meters. Remember that nano is the prefix for 10 to the minus 9. And C is 3 times 10 to the 8 meters per second. C is going to be lambda times F, so that means that F is going to be given by C over lambda. So the frequency of this light should be 3 times 10 to the 8 meters per second divided by 6.328 times 10 to the minus 7 meters, where I have taken this number that we got up here and basically moved the decimal over 2 spaces by taking this power and adding 2 to it. So now we should pull out the calculator, and it's 3 divided by 6.328, which gives us 0.474. So this is 0.474. The meters part, by the way, cancels, but we need to figure out the power. So it's times 10 to the 8 minus negative 7. And this is per second. So 8 minus negative 7 means that this thing right here is equal to 10 to the 15, and we need to actually move the decimal over by 1, so we subtract another 1, and you end up with frequency is approximately 4.74 times 10 to the 14 hertz. Okay, so as a quick double check for that, we might want to look at this figure 6.7 from Shipman, Wilson, Higgins, and Torr's Physical Science 14th edition. Again, this is figure 6.7. We got 4.74 times 10 to the 14. So the question is, does that fall somewhere in this visible range? Well, here's 4.3 times 10 to the 14. Here's 7.5 times 10 to the 14. So 4.74 times 10 to the 14 is in here somewhere. It is in fact red, as we suggested, so that's good news number 1. Good news number 2 is that it is in this visible range. So our double check suggests that we've done all of our math right. Therefore, a typical helium neon laser will radiate at about 4.74 times 10 to the 14 hertz, which is red. And I actually have one more significant figure here, because you can look up the speed of light and find out that it is, there's more significant figures, 2.997, etc. So the first 3 significant figures are actually 2.99, The next one is a 7, the next one after that's a 9. So if you wanted with 4 significant figures, you'd have rounded to 2.998. Let's work an example that has to do with sound intensity or intensity level. So how many times louder is 66 decibels than 60 decibels? Your textbook doesn't really give you an equation to go from one decibel level to another decibel level and figure out how many times louder you've gone. But it does give you this table 6.1, which is the sound intensity levels and decibel differences. And what we notice is that as you go up, for every 10 increase on the decibel scale, you also get 10 times louder. So this actually right here where it says 0 times louder maybe should say 1. It's basically just saying it's the same loudness as the threshold of hearing. If you go up by 10 decibels, then you get 10 times louder. 20 decibels, so you've gone 10 plus 10 is 100 times louder. 30 is 10 plus 10 plus 10, so that's 10 to the third or 1,000 times louder, and so on. And over here we notice that there's this little note in the bottom corner that says that a delta 3 decibel is a 2 increase. What that basically is saying is that for every 3 decibels that you add, you are getting 2 times louder than what you started with. Okay, so you're going 66 decibels from 60 decibels. How many times louder is that going to be? So 66 decibels minus 60 decibels gives us 6 decibels. And that is basically a delta, let's call it L for intensity level. Delta L is 6 decibels. So that is also the same thing as 3 decibels plus 3 decibels. And so this right here is 2 times louder. And this right here is another 2 times louder. So in total, you have 2 times 2 equals 4 times louder. So that's how you could solve for how many times louder the decibel level has gotten. So 66 decibels is about 4 times louder than 60 decibels. To get a more precise answer than that, you have to start using logarithms. Let's do another example that involves loudness and decibels and so on. So you have a noise of a jet taking off from 100 meters away, and you're told that it is 130 decibels. So this jet maybe makes 130 decibels as it's taking off from the aircraft carrier if you're the guy that's standing in the far corner-ish of the aircraft carrier. 130 meters is maybe 400 feet. Or, excuse me, 100 meters is about 340 feet. So we want to know how loud is it going to be from 200 meters away. So really getting closer to the other end of the aircraft carrier. Or maybe standing near the command tower, the conning tower. To solve this, you can use this ratio that says that I1 R1 squared is equal to I2 R2 squared. So solve for I2 because that's the intensity, which is related to the loudness. And basically we're given the R1 and the R2, and we're given something that pertains to the I1. So I2 is going to be R1 squared over R2 squared times I1. And one way of doing this, in fact, would be even to divide both sides by I1 and just set up a ratio. So this is going to give us a ratio between I2 and I1, and it's just going to be the square of these distances. So R1 was 100 meters, R2 was 200 meters, and if both the top and the bottom thing are squared, we can take the square outside of the parenthesis. So this basically looks like 1/2 squared, which is 1/4. So that's another way of saying that I2 is 4 times as intense, and therefore is going to be about 4 times as loud as I1. Okay, that's observation number 1. Observation number 2 is that a delta of 3 decibels is the same thing as going 2 times as loud. And that means that if you subtract 3 decibels, you're getting half as loud. In other words, 2 times as quiet. So I1 corresponded to 130 decibels. Therefore, we need to get a quarter as loud, so that means that we need, between these two statements, to get 6 decibels less. So I2 is 6 decibels less than I1. So I1 was 130 decibels. That means that I2 should be 130 minus 6, 124 decibels. So that means that the noise from 200 meters away is about 124 decibels. Okay, let's go to a football game. So at a certain football game, you've got a 90 decibel noise level in the stadium 10 meters from the sideline. So the question is, assuming that no energy is lost in the air, how far away can this game be heard? So we're talking 90 decibels to somebody who's standing right here. By the way, for this game in question, it's a whole lot more than 90 decibels. So how far away can the game be heard? We'll take the threshold of human hearing. So 0 decibels is threshold for human hearing. And that again is coming from that table 6.1 of your Shipman, Wilson, Higgins, and Torres physical science text. And what we've been told is that it's 90 decibels at 10 meters from sideline. And we'll take as a rough estimate that the sideline is basically where the source is located. That's not necessarily true, but if you have a nice symmetrical seating arrangement in your stadium, roughly the middle of the field may sound to somebody standing outside the field like it's the source of the noise. So this is not a terrible estimate. Basically, we want to know how far away do you have to be, how far, and that would be R2, for I2 to go to 0 decibels. Okay, and at 90 decibels to 0 decibels, that means that R2 squared over R1 squared is going to be I1 over I2. Okay, this is just rearranging from I1 R1 squared equals I2 R2 squared. So I1 over I2 is going to give us what? Well, it's going to give us the ratio of the loudness at the distance R1. So this right here is equivalent to I1. This right here is equivalent to R1. This right here is equivalent to I2, and we're solving for R2. So this ratio is the ratio that you get from 90 decibels over 0 decibels. So 90 decibels over 0 decibels is equivalent to doing a factor of 10 to the 9th. Again, you can get that by looking at this table 6.1, sound intensity levels and decibel differences, from the Shipman, Wilson, Higgins, and Torres physical science text. So 90 decibels versus 0 decibels, this is threshold of hearing. This is 10 to the 9 times larger than threshold of hearing. So what this whole thing is saying is that I1 over I2 is equal to 10 to the 9. Okay, well, we're trying to solve ultimately for R2. So R2 squared is I1 over I2 R1 squared. And what that means is that R2 is the square root of I1 over I2 times R1. So I've basically taken a square root of everything on both sides. Alright, so this is square root of 10 to the 9th times 10 meters. So let's see what we get when we plug that in. So to put in 10 to the 9th on my calculator, I put in 9 10 to the x. So here's 10 to the 9. I take a square root. I multiply by 10. And I get that you can still hear it 316,000 meters away. So I just got that R2 is 316,000 and 227.7, so we'll call it 228 meters. So that's pretty far away. That's, 320,000 meters away is 320 kilometers. Obviously, what this tells us is that there tends to be some loss in the energy that propagates out from a source as it propagates through the air. Because obviously you cannot hear a sports game when it is 320 kilometers away. That would be like, since we're in Troy, that would be like being able to hear Alabama or Auburn when they're playing against, say, LSU while sitting in Troy. Obviously, you can't quite do that. Maybe not quite so far away as LSU, but maybe so far away as Mississippi or Mississippi State. That's still quite far away. So quite a bit of this sound energy is obviously being damped out of the air over long distances. Similarly, you obviously cannot hear a jet airplane while it's flying overhead at its cruising altitude. You can look up all the time and see the little jet contrails, and you don't necessarily hear the jet, even though you know that that jet is 130 decibels if you're standing nearby. Our next example has to do with resonances. So the 11th example for chapter 6, we take a 256 Hertz tuning fork, we strike it, we place it at the opening of a vertical tube whose water level can be varied from 0 meters to 1 meters, as measured from the top of the tube. So 0 meters means the water level is here at the top of the tube, 1 meter means the water level is down here at the bottom of the tube. And what we want to know is, what water levels will this tuning fork be resonant with the tube? Resonant basically means that an antinode is present at the opening of the tube. So this diagram actually is showing what's going on during resonance. Since sound waves, like other waves, can be described as basically sine waves, what this means is that the nodes and antinodes are going to occur at even increments. So for the nodes, every m times lambda over 4 will be a node, and that's m is any even integer. So m equals 2n, where n is an integer. And for the antinodes, you get 1 every p times lambda over 4, where p is any odd integer. So that is to say, p is equal to 2n plus 1, and n is any integer from 0 on up to as high as you want. So what that means is we're using a 256 Hertz tuning fork. So we've been given that F is 256 Hertz. And we know that V is F times lambda. So that means that lambda must be V over F, where V is 344 meters per second. That's given because it's a sound wave. Okay, so that basically means that what we're going to end up getting is that lambda is equal to 344 meters per second divided by 256 Hertz. So out comes the calculator. 344 meters per second divided by 256 Hertz gives us 1.34375 meters. So 1.34375 meters is the wavelength. Now this right here is the condition that we need for any antinode, and that basically is when the thing is at resonance. So resonance is going to occur, for example, at 1 lambda, 3 lambda, 5 lambda, 7 lambda, all over 4, of course. All right, so the next question that is applicable to this problem is, which of these lengths, so these are the lengths for resonance, which of these lengths fulfills the requirement that L is less than 1 meter, because the tube is only up to a meter deep. So we can pull out the calculator and start calculating. So this thing divided by 4 gives us 0.3359. So we'll go ahead and round that to 0.334. So L equals 0.334 meters. Okay, the next one that we get, so go ahead and get back to that number we started with, it would be this. So we need to multiply this by 3. Now divide that by 4. And so the next time that resonance occurs is for 1.007 meters. So that we might round to, 1.008. So this would be first resonance. Second resonance is 1.008 meters. Third resonance is going to occur for, so divide this thing by 3, multiply by 4. Here's the wavelength again. So multiply by 5. So this is to get the third resonance. Divide that by 4, and it's 1.6796. So 1.680 meters. So of all of these, only one of them satisfies the condition that the length has to be less than 1 meter. What that means is that resonance will occur at x equals 0.33, should be 0.334 meters. I guess depending on where you round, you could get 0.336 meters. Usually if it's within about 1%, it's right, so this is fine. And then the next resonance, you need a longer tube to get. The 12th example that I want to work for this chapter is about a well. So you have a well, and you know that the depth of the well is 25 meters. And the question is, what is the minimum frequency which will produce a loud resonance in this well? So again, if you want to get a loud resonance, you need to have an antinode appearing at the top of the tube, or in this case, at the top of the well. So you need to have an antinode occurring here. The other rule with these nodes and antinodes is that there will always be a node at the very bottom of the well, the point where the sound wave is actually being reflected from. Okay, so again, we're going for some version of this condition where p times lambda over 4 is equal to the length of the well. So these are both equal to length, and that's to solve for nodes or for antinodes. We want an antinode. Okay, so in order to get the frequency, we have to remember that frequency is equal to the speed over the wavelength. That's just a way of rearranging that speed is wavelength times frequency. So the shortest frequency is going to yield the longest wavelength. And the question is, what is the minimum frequency to get a loud resonance? So that basically means we're solving for what lambda is the longest, which gives resonance. Okay, and then convert that, then convert to frequency. And that's going to be shortest frequency. So to do that, it might help us to draw a little diagram of the well as a resonance tube. So for the longest possible wavelength that will actually produce resonance, we need to have the wave doing something like this, where this guy right here is the antinode. And recall that this antinode first occurs, so this wavelength thing will come up here and it'll make another antinode and another node. The whole wavelength is going to be like this. this right here is actually a quarter of this wavelength. Obviously, it's not drawn to scale. So P equals 1, and therefore L is equal to lambda over 4. L is 25 meters was given because it's the depth of the well. And so what we're solving for here then is lambda. So lambda has to be 4 times L, which is 4 times 25 meters, which is 100 meters. Okay, so that's the wavelength for which that's the longest wavelength for which resonance can be produced in this well. So now we've got to figure out what frequency goes with that. And again, frequency is is V over lambda. So that's going to be 344 meters per second because it's a sound wave, divided by 100 meters because that's what we just solved for. So that means that the frequency that should be the shortest frequency for which you can get resonance out of this well is 3.44 per second, or 3.44 hertz. So the minimum frequency which you can use to produce a loud resonance in this well is 344 hertz. Now, if you have something that's higher frequency, you can also produce resonances. For example, if you have 6.88 hertz instead of 3.44, you should be able to get some resonance out. But nothing shorter, or nothing lower frequency than 3.44 hertz should give a sound out. Now, with that said, the threshold of human hearing is often around 10 to 20 hertz. So this is what will produce a loud resonance in the well. But if you want to actually be able to hear that loud resonance, you may have to go to higher frequency than this. That's all the examples that I have for this chapter. Thanks for watching, and I hope that you found all of these helpful.